Now we are going to another important theorem, that is uniform continuity theorem. That's a well-known theorem. The theorem known as uniform continuity theorem. Uniform continuity theorem. So, what is uniform continuity theorem? The theorem states that letter A is a part of R, or letter not A is a part of R. Let I be an interval. Let I be an interval, comma, which is closed and bounded. Closed and bounded. F from I to R, F from I to R is continuous function on I. Is continuous function on I. Then F is uniformly continuous on I. Then F is uniformly continuous on I. This is uniform continuity theorem. I is an interval which is closed and bounded. So this is the crucial point here. Closed and bounded. Closed means it consists of all of its limit points. And F is defined from where to where I to R, which is a continuous function. Then F is uniformly continuous on I. So the summarized as that we know that uniform continuity always implies continuity. The relation between uniform continuity and continuity. Uniform continuity always implies the continuity. But the reverse inclusion need not be true. A continuous function will not be a uniformly continuous function. But this uniform continuity theorem ensures that the continuity of a function should imply uniform continuity only when that function is defined on closed and bounded interval. So a continuous function is a continuous function. This is summarized as a continuous function on a closed and bounded interval should imply uniform continuity. We know that uniform continuity always implies continuity, but continuity need not be implies uniform continuity. So under this condition, a continuity should imply uniform continuity only when that continuous function is defined on where closed and bounded interval. Okay. How to prove this one? The proof is done by contradiction method. Assume F is not uniformly continuous. Assume F is not uniformly continuous. It is given F is continuous, defined on I is closed and bounded, and our task is to prove F is uniformly continuous. But first we assume that F is not uniformly continuous on I. Then F is not uniformly continuous on I. Then by non-uniform criteria, there exist two sequences, xn and un in I, such that limit of xn minus un equals 0. Limit xn minus un equals 0, and the modulus of f of xn minus f of un greater than or equals some epsilon or epsilon naught, where epsilon naught is positive. So this is obtained how? Why? Because of our non-uniform criteria. Since our assumption is F is not uniformly continuous, so by non-uniform criteria, there exist two sequences xn and un fall in I with a limit xn minus un equals 0 and a modulus of f of xn minus f of un greater than or equals some epsilon naught, where epsilon naught greater than 0. Now put on. Limit xn minus un equals 0. Limit xn minus un equals 0 means there exists some epsilon positive such that modulus of xn minus un is strictly less than epsilon. Okay, epsilon is positive. Limit xn minus un equals 0. Instead of delta, we use epsilon here. Mod xn minus un strictly less than epsilon. So for more convenience, put epsilon equals 1 by n. When epsilon equals 1 by n, it is a modulus of xn minus un strictly less than 1 by n. For all n fall in n. For all n fall in n or n greater than or equals k. There exists a for all n greater than or equals n and n greater than or equals k for where k is a natural number. Okay. But what is xn? Xn is chosen from where? Xn is chosen from I. What is I? I is a bounded interval. Since I is bounded, secant xn is bounded. Secant xn is bounded because I is bounded. But by Bolzano-Weierstrass theorem, a bounded convergent sequence has a xn is bounded, then this xn has a convergent subsequence. Xn has a convergent subsequence. Let it be sequence xnk. So xnk be a convergent subsequence of which one? Xn. Xnk be a convergent subsequence of xn. So xnk is a convergent subsequence means limit xnk exists. So let's suppose limit xnk equals z. Limit xnk equals z. But what is xnk? Xnk be a subsequence of xn. Xn is chosen from where? I. So clearly this xnk falling where? I. But what is I? I is closed means I consists of all of its limit points. Since I is closed, I consists of all of its limit points. Therefore, z is a limit. Since z is a limit point of x and k, then surely z fall in I. Let limit xnk equals z. So clearly, since xnk is a subsequence of xn, since xn fall in I, xnk fall in I is closed, means I consists of all of its limit points, therefore z fall in I. Agree? Okay. So, now consider, suppose f is continuous, or even, before going to that one, what is the modulus of unk minus h? Modulus of unk minus h. Modulus of unk minus h equals modulus of unk, where unk be a subsequence of un. So, mod unk minus xnk plus xnk. Okay, plus xnk. Modulus of unk minus h equals mod unk minus mod minus xnk plus xnk. That means it is less than or equals mod unk minus xnk plus mod xnk. Agreed? Okay. Xnk converges to z. Xnk converges to z. So the corresponding subsequence unk also converges to where? Z. Therefore, mod unk minus h converges to where? 0. So clearly, mod unk minus h, modulus of or unk, sequence unk also converges to where? Z itself. Okay, unk also converges to z. By unk minus xnk goes to 0. Agreed? And so on. So unk also unk minus h. Unk converges to z because modulus of unk minus h equals modulus of unk minus xnk plus xnk, which is less than or equals modulus of unk minus xnk plus mod xnk. This goes to 0. Why? Because limit xn minus un equals 0 remains modulus of xnk, but it converges to where? Z itself. modulus of x and k. So finally, modulus of u and k converges to set. So u and k converges to set. So u and k converges to set, limit x and k also set. So x and k converges to set means x and k converges to set, also u and k converges to set. But what is f? F is continuous. It is given f is continuous. F is continuous on I. So this should implies f of x n converges to where? F of x and k converges to f of z, and f of u and k also converges to f of z. Okay. Now consider modulus of f of x and k. Now consider modulus of f of x and k minus f of u and k. Modulus of f of x and k minus f of u and k. So which is less than or equals modulus of f of x and k, or which is equals modulus of f of x and k minus f of z plus f of z minus f of u and k. Okay, so that means this gives modulus of f of x and k minus f of u and k, which is less than or equals, by the triangular inequality, it is modulus of f of x and k minus f of z, modulus of f of x and k minus f of z, plus modulus of f of u and k minus f of z, or modulus of f of z minus f of u and k. We know that f of x and k converges to f of z, f of u and k also converges to f of z, so these two are goes to 0. That means it is strictly less than some epsilon. Okay, that means modulus of f of x and k minus f of u and k less than epsilon means f is uniformly continuous on I. That's a contradiction. This contradiction is due why? Because modulo we know that f of x and k minus f of u and k greater than or equals epsilon naught, but here it is less than epsilon. That's a contradiction. This contradiction is due to our wrong assumption. Therefore, f is uniformly continuous on I. So this is the uniform continuity theorem. The theorem is very important. That's a well-known result. Means the continuity on a closed and bounded interval always implies the uniform continuity. That is the summarizing this theorem, and the proof is depends upon our non-uniform criterion arguments, and finally we reach a contradiction. Okay.